Welcome to the video on projectiles launched at an angle. This diagram shows a projectile launched at an initial velocity with some angle theta. The initial velocity has a horizontal and vertical component represented by the vector arrows. First, let's study the shape of the trajectory. This shape is a parabola. Notice if the object were launched horizontally at the top, that shape would give the half parabola. Next, let's look at the horizontal and vertical velocity vectors separately. First, studying the horizontal vectors. Notice that they remain the same length throughout the trajectory. This means that the horizontal component of the velocity remains constant. If there is no change in horizontal velocity, that tells us that the horizontal acceleration is 0 meters per second squared. Next, let's look at the vertical vectors, specifically on the way up. Here is our initial vertical velocity. Notice how those vectors get smaller and smaller. This tells us that vertically, the object is slowing down on the way up until at the very top, the y component of the velocity is 0. It's important to note that at the top, the object is still moving because it has a horizontal component of the velocity. It has only stopped moving vertically, so it can come back down. On the way up, we see these vertical components decrease because the object slows down due to the acceleration due to gravity. We can also study the object in the second half of the trajectory on the way back down. Notice that these vertical velocity vectors increase and the object begins to fall faster and faster. That is because the acceleration due to gravity increases that vertical velocity on the way back down. It is also important to note that the trajectory of an object launched at an angle is symmetrical. So the velocity at each of these points on either side of the parabola are equal to one another. So if the object is launched with a velocity or a speed of 45 meters per second and lands at the same height, it will land with a velocity of negative 45 meters per second or a speed of 45 meters per second. I would like you to think through this question. A zookeeper devises a rubber band gun to shoot food to the monkey who is too shy to come down from the trees. If the monkey does not move, should the zookeeper aim above, at, or below the monkey? Then, if the monkey lets go of the branch at the instant the zookeeper shoots the food, should he aim above, at, or below the monkey mid-air? Please pause the video now and think of an answer to these two questions. Hopefully you came to the conclusion that as the monkey stays still, the zookeeper should aim above the monkey. That's because objects do not travel in diagonal lines noted by the dotted line on this diagram. The acceleration due to gravity pulls objects down as they fall. So because the banana will fall as it's shot, the zookeeper needs to aim above the monkey. Second, if the monkey falls when the banana is shot, the zookeeper should shoot or aim the banana right at the monkey. Because all objects fall at the same rate, the banana and the monkey will collide at some point in the air. The range is the horizontal displacement of a projectile launched at an angle when it launches and lands at the same height. The basketball player is an example of a range. The ball is released from his hands at the height of the hoop. Because the total vertical displacement is 0, the horizontal displacement is considered a range. Looking at the second diagram, this object launched, I believe it was a pumpkin, has a vertical displacement of -10 meters. The object still has a horizontal displacement, but this is not considered a range because the object does not start and land at the same height. When objects are launched at an angle, in order to achieve the maximum range, they must be launched at 45 degrees. There are pairs of angles that will result in the projectile being launched at an equal range. These angles are complementary angles, or angles at up to 90 degrees. So this means that an object launched at 30 degrees and 60 degrees will land in the same spot, or an object launched at 25 degrees and 55 degrees will land at the same spot. This is described in the diagram of a golfer. So notice if the golf ball were to be hit at a 45-degree angle, that would give the maximum range. If the golf ball were to be hit at 15 degrees or 75 degrees, it would land in the same spot, meaning they would have the same range. That is the same for 30 and 60 degrees. It's important to note that objects that are launched at the complementary angles have the same range, but they do not have the same time travel or the same maximum height. Of course, the object launched at 75 degrees will be launched much higher than an object launched at 15 degrees, and it will take more time to come back down.